Hello, I'm Tatiana Mayskaya, and I'm going to present my paper entitled as Dynamic Choice of Information Sources. Have you ever wondered why in any air crash investigation, throughout the whole investigation, the focus is always on the most likely cause of an accident, such as pilot error, poor maintenance, or a terrorist attack? Wouldn't it be optimal first to rule out a more troubling cause, such as a design fault? For example, in 1996, a Boeing 747 exploded and crashed into the Atlantic Ocean short after takeoff from JFK Airport. It was the third deadliest aviation accident in the US history, and a lot of attention was drawn to its investigation. Initially, eyewitness accounts led many to believe the cause of the crash was a bomb or surface-to-air missile attack. At the same time, one cannot immediately rule out other possible causes related to mechanical failure. It was extremely important to find out what happened because there were so many 747 planes at the time, and if there was a fault in the plane design, other planes were at risk of repeating the same fate. Yet, despite the immense importance of ruling out a design fault, the investigation team followed their prior beliefs and focused more on the bomb theory. As the National Transportation Safety Board does not investigate criminal activity, it had to join forces with the FBI. The investigators spent weeks carefully searching for any sign of foul play. They were looking for something that would support any kind of missile or a bomb. They found no signs of explosive device. At that point, the NTSB team shifted their attention to the design fault version, while the FBI continued to explore the possibility of a terrorist attack. 16 months later, the FBI announced there was no evidence of a criminal act, and they closed the active investigation. Meanwhile, the NTSB team continued to explore the design fault version. They went as far as assembling the wreckage and eventually reconstructing the whole aircraft. Their efforts were not in vain. It took them 4 years, but they found the flaw in the design. Their discovery shocked the industry and fundamentally changed the way the aircrafts are designed. In the airline industry, accident investigators face the trade-off. On the one hand, they want to rule out a design fault that has major consequences for the industry, as it was with the recent grounding of the Boeing 737 MAX. Changing the design completely prevents similar accidents in the future, which otherwise were inevitable. On the other hand, the investigators want to find instances where current safety policies were insufficient or inadequate to prevent terrorist attack, pilot error, or poor maintenance. The last cause is less consequential for the industry because the best we can do is to improve procedures, but these measures have limited effect as they only lower the probability but never completely prevent similar accidents in the future. However, human factor is much more common in aviation, which makes it ex ante the most likely cause for the majority of uninvestigated accidents. I show that the investigation timeline in an example was optimal. At the beginning of the investigation, it's optimal to focus on the most likely cause of the accident, such as terrorist attack. In the absence of finding, the belief reached the point where a design fault version becomes an equally plausible hypothesis. At this moment, it's optimal to split the resources between the two hypotheses. As the investigation continues without a finding, at some point, it's optimal to direct all resources towards searching for confirmation of a design fault, which is the most consequential hypothesis. This learning pattern explains how the consequences versus belief trade-off is optimally resolved. The beliefs drives the direction of the search at the beginning of the investigation. At the end of the investigation, the focus shifts towards eliminating the cause which has measured consequences for the society. The exact time of the shift in the priorities depends on the importance of the investigation. The more important it is for the society to learn the true cause, the later the shift. Besides air crash investigations, there are many other environments that our agent faces the beliefs versus consequences trade-off. Should a doctor test for a more likely disease or a more serious one? Should a researcher test a more plausible or a more controversial and exciting hypothesis? Should a voter listen to media sources that confirm his current political views or sources that challenge them? In each of these examples, the agent faces a trade-off between choosing an information source that produces conclusive evidence with higher probability, such as testing for a more likely disease or searching for belief-confirming facts, and a source whose evidence is less likely but more important if confirmed, such as testing for a more serious disease or searching for belief-contradicting facts. I amend the optimal stopping problem with the second information source. In contrast to rational and attention literature, the agent's choice is restricted to two predefined sources, and the cost of information acquisition is prior independent. Many authors focus on so-called myopic strategies, that is, strategies that maximize the next period payoff while neglecting dynamic considerations. The computer science literature proves the asymptotic optimalities of myopic strategies. In microeconomic theory, the myopic strategies are found to be sometimes optimal, but in environments that are quite different from mine. In my model, the optimal strategy does not have to coincide with the myopic strategy. On the contrary, the optimal strategy features the farsightedness of the agent when he follows his beliefs and does not investigate the most consequential hypothesis, which is, by its nature of being the most consequential, is also a myopically optimal one. In Pandora's box problem, the agent faces a series of options or boxes, which he samples sequentially, each time fully learning the payoff from a sample option. In contrast, in my model, the agent faces only two hypotheses, and it takes time to learn whether they are true or not. There is a close relationship between what I'm doing and the multi-arm bandit literature with Poisson bandits. The main conceptual difference of my model is that the payoff does not come from the discovery itself, but rather from the action the agent takes after he stops learning. The discovery triggers the decision, and hence the agent immediately gets the payoff, which makes my model mathematically similar to bandit literature. However, the agent sometimes stops learning and gets the payoff without making the discovery, which is impossible with multi-arm bandits. In reality, learning is a mixture of gradual collection of information and sudden breakthroughs. I assume pure breakthrough learning, which places my paper in line with papers that adopt the Poisson framework. The two papers that are closest to mine are by Irina Nikandrova and Roman Spanks, published in Theoretical Economics in 2018, and by Jan Kuche and Konrad Meierdorf, published in American Economic Review in 2018. Neither of them focus on belief versus consequences trade-off. Nikandrova-Spanks assumes the two hypotheses are being independent and of equal importance, which shuts down the consequence considerations. She and Meierdorf assume the two hypotheses are exhaustive, so that the true cause can always be found through available information sources. These assumptions limit possible learning patterns to the extent that they never get the strategy that clearly features two phases of learning, testing the most likely hypothesis during the first phase and testing the most consequential hypothesis during the second phase. In particular, in their model, if the agent optimally splits resources between the two hypotheses, he never gives up learning without a discovery, thus never shifts to the second learning phase. First, I present a model where two hypotheses are mutually exclusive. Then I extend the model by including the possibility when both hypotheses are correct. The paper studies a decision problem. An agent's objective is to take an action out of a finite set. In a plane crash example, these actions would be measures taken to prevent future accidents, such as improving an aircraft design, changing security protocols, adjusting training procedures for pilots. The agent's utility from each action depends on the true state of the world. In the example, the true state is the true cause of an accident, which defines how effective the taken measures are. There are three states, which I code as 0, 0, 1, 0, and 0, 1. Later, I extend the model to include the false state 1, 1. So the state of the world is a vector with two binary components. Each component corresponds to a hypothesis, which can be either true or false. Before taking an action, the agent can learn about the state by, for example, conducting an investigation. Learning is modeled as a search for confirmation that a hypothesis is true. There are two hypotheses, hence there are two search directions, for state 1, 0 and for state 0, 1. In other words, there are two information sources, one for each state component. Since the search can be successful only if the corresponding hypothesis is true, it's impossible to find confirmation for state 0, 0. And this assumption reflects the spatial nature of state 0, 0. This state encompasses all other hypotheses for which it's impossible to find the proof. When the agent uses an information source, he observes a Poisson process that generates confirmation with rate equal to the corresponding state component. For instance, if he searches for state 1, 0, he receives a confirmation with rate 1 if the first hypothesis is true, and he never receives a confirmation if the first hypothesis is false. Learning is costly. The floor cost of learning is 1. The agent can stop learning at any moment and take an action. His total payoff is his utility from the action minus the cost of learning. As the floor cost is 1, the cost of learning is equal to the total time the agent spends on collecting information. As clear from the agent's payoff, there is no discounting. This assumption plays a role in the result, as I will explain later. While the agent still learns, each moment he decides how to allocate a unit of his attention between two information sources. The amount of attention defines the rate at which the agent receives the confirmation of a corresponding state component is 1. The more attention the agent allocates to a source, the higher the rate. Hence, the more informative the source is about the corresponding state component. For the leading example, suppose there are two mutually exclusive, well-articulated possible causes of an accident. The first cause is related to human factor due to poor procedures for pilots, maintenance, or security personnel. Poor procedures lead to pilot error, bad maintenance, or terrorist attacks. This cause corresponds to state 1, 0. The second cause is a design fault in an aircraft, as it was with Boeing 747 exploded over the Atlantic. This cause corresponds to state 0, 1. It can also be the case that the true cause of an accident is unexplained human behavior, which corresponds to state 0, 0. Essentially, this state encompasses all other causes for which it's impossible to find the proof. For example, there are several cases where investigators excluded all possible causes except for one, and were forced to conclude that a pilot committed suicide by deliberately crashing the plane, as happened in the French Alps in 2015, in Namibia in 2013, and possibly in Indonesia in 1997. Another example is the disappearance of Malaysia Airline Flight 370, which has been described as one of the biggest mysteries in modern aviation history. A leading theory is that someone in the cockpit reprogrammed the aircraft autopilot to travel south across the Indian Ocean, where the plane evidently ran out of fuel and crashed. We can never be sure why the pilot did such a terrible thing. Hence, in contrast to other causes, we can neither confirm such cause with certainty nor prevent similar accidents in the future. Suppose there are 3 possible actions the investigators can take. Improve operating training and maintenance procedures for pilots, maintenance, and security personnel. Recommend appropriate changes in the design of the aircraft, or do nothing. The utility from the appropriate measures is positive and denoted as better. I assume that doing nothing is optimal if the true cause is unexplained behavior, because any serious changes either in the plane design or in pilots' training procedures are costly for the industry. Failure to implement the right measures leads to zero utility in all cases except for one. If the accident is caused by a faulty aircraft design and nothing is done, the utility loss is kappa. Hence, parameter beta is responsible for the general importance of the investigation, while parameter kappa creates the asymmetry between the two hypotheses and amplify the consequences of a design fault. Suppose beta is sufficiently large, that is, the investigation is important, and kappa is relatively low, that is, the asymmetry between the causes is not too high. For this range of parameters, the optimal strategy is as follows. Once the true cause is found, the investigation is stopped. If the true cause is found to be poor procedures, the optimal action is P, that is, improving procedures. If the true cause is found to be a design fault, the optimal action is D, that is, making changes in the design. In the absence of finding, the investigators follow some deterministic attention allocation plan, which I'll now describe. Following statistics, let's assume that the poor procedures hypothesis is more likely than a design fault, so that the prior belief about state 1, 0 is higher than the prior belief about state 0, 1. In parallel, I'm going to demonstrate the optimal belief trajectory on the belief space that forms a triangle with corners corresponding to different states. 0, 0 point corresponds to unexplained behavior, 1, 0 point corresponds to poor procedures, and 0, 1 point corresponds to a design fault. We start at some point below the diagonal because, by assumption, the poor procedures version is more likely. At the beginning of investigation, it's optimal to focus on more likely cause of an accident, which is the poor procedures version in our case. That means the investigators search for evidence and facts that confirm the initial hypothesis that the accident was the result of poor procedures. In other words, we use source 1. In the absence of confirmation, the investigators update their beliefs towards other causes. That means they become more pessimistic about poor procedures hypothesis, and at the same time, they become more optimistic about the design fault hypothesis. At some point, the beliefs become equal. This is the point where the belief trajectory reaches the diagonal. At this moment, it's optimal to adjust the focus of the investigation in a way that the belief trajectory moves along the diagonal. This is done by splitting the resources equally between the two hypotheses. In the absence of confirmation for either of the two causes, the investigators become more pessimistic about both hypotheses, and their beliefs drift down towards the state where the true cause of the accident can never be confirmed with certainty. At some moment, it's optimal to change the focus again and direct all resources towards searching for confirmation of a design fault. The beliefs are updated towards the poor procedures and the unexplained behavior hypothesis. That means the belief about the poor procedures goes up, while the belief about the design fault goes down. I denote by T star the time when the focus shifts from joint learning from both sources to source 2. This is the time when the probability of the design fault version is the same as the probability of the poor procedures version, and this probability is uniquely defined by a certain equation that you can see on the slide. I'll come back to this equation later. In the absence of finding, the investigation continues until the probability of a design fault version is as low as 1 over beta plus kappa. If the true cause remains unidentified at the end of the investigation, the optimal action is doing nothing. There are two properties of this optimal strategy that I want to highlight because they can be generalized beyond this example to all decision problems that describes in the setup. The first property concerns the general learning pattern, and it says that the optimal strategy has a two-phase form. The second property speaks to how the optimal T star is defined, and it says that the more important the investigation, the longer the first phase. For any action space, any utility function, and any prior, the optimal strategy has a two-phase form. That means there are two time thresholds, T star and tau bar, that separate two phases of the learning plan. In the absence of confirmation, the agent stops learning at tau bar and takes some action A. During the first phase, The agent always chooses the source that produces a confirmation with a higher probability. In other words, he focuses on his beliefs and searches for a confirmation of a more likely hypothesis. During the second phase, the agent devotes his full attention to one source, say source K, and he never changes the source. Thus, he keeps searching in the same direction throughout the whole phase. According to the theorem, the optimal strategy belongs to the class of two-phase form strategies. That means it's sufficient to optimize over the time thresholds T star and tau bar, the source K that the agent uses during the second phase, and action A he takes at time tau bar. As the second phase is the final phase of learning, the agent focuses on consequences and therefore chooses source K in such a way that it maximizes the effect of confirmation on the taken action. In the example, the consequences of not making changes in the design, if the design was indeed faulty, could be catastrophic, which captures by parameter kappa. Hence, K was equal to 2 in the example. And so it's optimal to focus on the design fault version at the final phase of the investigation. This learning pattern explains how the consequences versus beliefs trade-off is optimally resolved. The beliefs drives the direction of the search at the beginning of learning. If the search remains unsuccessful for sufficiently long time, the focus shifts towards eliminating the state that has measured consequences for the decision. A learning pattern of a two-phase strategy has three distinct parts. First, the agent pays attention to one source. Then he switches to using both sources simultaneously. And finally, he ends with using a single source again. The sources at the beginning and at the end could be either different or the same. Moreover, the first phase can end before the beliefs become equal. And so the agent never uses both sources simultaneously. Or one of the sources might never be used, or the stopping time could be 0. Which of these learning patterns is optimal depends on the prior beliefs and the utility function that defines how much the agent gets from each action in each state. The intuition behind the two-phase form strategy is based on backward induction reasoning. I start with any strategy and show that if the strategy is optimal, it must have a two-phase form. Clearly, there exists a moment, possibly infinite, when the agent stops learning in the absence of confirmation. Just before that moment, he uses some source. Going back in time, one can always find the latest moment when the agent devotes at least some attention to the other source. Denote this moment as T star. It could also be the case that just before stopping, the agent splits his attention between two resources. Then, at this case, T star coincides with the stopping time. Note that so far, I didn't use the assumption that a given strategy is optimal, and everything I said is true for any learning plan. By definition of the class of two-phase form strategies, during the second phase, the agent devotes his full attention to one source. By construction, T star is the earliest time after which the agent uses only one source. Hence, the learning interval after T star can be taken as the second phase. If T star is 0, I already get the two-phase form, where the first phase has 0 length. So suppose T star is positive. I need to show that if the strategy is optimal, the attention rule before T star is the first phase rule, where the agent always chooses the source that produces a confirmation with a higher probability. That means if state 1,0 is more likely than state 0,1, then the agent pays full attention to source 1. If state 0,1 is more likely than state 1,0, then the agent pays full attention to source 2. If these two states are equally likely, the agent splits his attention equally between the two sources. By construction of T star, if T star is positive, the agent has both sources in his learning plan. Fixing the total amount of attention devoted to each source, the agent faces the problem of ordering the sources. I need to show that as long as the agent has both sources in his future learning plan, it's optimal to start with the source that produces a confirmation with a higher probability. I show it through a deviation argument. Consider two subsequent time intervals of the same length delta. Think of delta as being infinitesimally small. Let's compare two learning plans that coincide everywhere in the gray area and differ only within these two time intervals. According to the first plan, the agent pays full attention to source 1 during the first interval, and he pays full attention to source 2 during the second interval. The second plan exchanges the order of the sources. To calculate the expected benefit from exchanging the sources, consider three scenarios. If neither source produces confirmation during the intervals, both sources get the agent's attention anyway, and the change of the order does not affect the realized payoff. Hence, the agent is indifferent between which sources to use first, and so the benefit from the exchange is zero. If source 1 produces confirmation, the agent never reaches the second source in the first plan, which saves him the cost of using that source. Hence, the benefit from the exchange is negative and equal to minus delta, where delta is the cost of using source 2 during a time interval of length delta. This scenario happens with probability equal to the prior belief that the source 1 is the right source times the probability that the right source produces confirmation during time interval of length delta. The third scenario is symmetric to the second one. If source 2 produces confirmation, the agent never reaches the first source in the second plan, meaning that the benefit from the exchange is positive and equal to delta, the cost of using source 1 during the time interval of length delta. This scenario happens with probability equal to the prior belief that source 2 is the right source, times the probability that the right source produces confirmation during time interval of length delta. The expected benefit from the exchange is positive if and only if state 01 is more likely than state 10. That proves the optimality of the first phase rule. If for each moment t, if the current belief are such that state 10 is more likely than state 01, it's optimal to pay full attention to source 1 at this time t. If state 01 is more likely than state 10, it's optimal to pay full attention to source 2. Summarizing this intuition, following the beliefs is optimal because it's the best way to minimize the expected learning cost. Note that this logic works only when the agent has both sources in his future learning plan, that is, before moment t star. I assume there is no discounting. Although I do not have formal results with model with discounting, I can conjecture how discounting would have affected the results. If there had been discounting, the time when the agent takes action would have mattered. That affects the benefit from the exchange in scenarios 2 and 3. In scenario 2, in addition to extra cost from using the wrong source, there is a delay in taking action, which decreases the utility from this action. In scenario 3, in addition to saving costs by using the right source first, the agent gets a higher utility from the right action because he takes this action earlier. That means the first phase rule would have been different and included the utility function together with the current beliefs. Hence, discounting just blurs the distinction between the phases from the point of how they resolve the beliefs versus consequences trade-off. Now, let's move to the second property that can be extended to the general model. In the example, the length of the first phase increases as we increase parameter beta, which accounts for the importance of the investigation. We can see it from this equation. The right-hand side increases in beta, the left-hand side decreases in belief P. Hence, P decreases in beta. In the absence of finding, the agent becomes more pessimistic so that the belief decreases in time t. Hence, time t star increases in beta. That explains why in almost any aircraft crash investigation, the focus is always on the most likely cause of an accident. The cost of an accident is very high in the airline industry, so that it's extremely important for the society to determine the exact cause of each accident to prevent future accidents. Hence, beta is high. According to the model, large beta implies the first phase is long. Long first phase means that the true cause is often found before the second phase is reached, so that throughout the whole investigation, the focus is always on the most likely cause of an accident. I extended this result to the general model. Loosely speaking, when the utility function is such that the loss from taking a wrong action is high, or in other words, when the stakes are high, the first phase will be relatively long. Formally, for any prior beliefs and any time t star, there exists a lower bound on the loss from taking a wrong action, such that the first phase lasts at least time t star. So far, I was talking about the model with three states of the world: when only hypothesis 1 is true, when only hypothesis 2 is true, and when both of them are false. Now I'll extend the model to the false states, state when both hypotheses are true. The model with three states restricts the hypothesis to be imperfectly negatively correlated, meaning that at most one of them can be true. A plane crashed either because of poor procedures or because of design fault. An infection can be either bacterial, that is caused by bacteria, or viral, that is caused by viruses. However, depending on the hypothesis, their mutual exclusivity could be a rather strong assumption. For example, both bad weather and human factor could potentially contribute to an accident, so that these hypotheses are not mutually exclusive. A stroke can be caused by malfunctioning of both cardio and neurosystems. With four states, the optimal strategy also has a two-phase form that is characterized by two time thresholds, the action taken at the end of phase 2, and the source used during the second phase. The only conceptual difference is the first phase rule. To formulate this rule, I need to introduce one notation. In contrast to three-state case, the first confirmation does not fully reveal the state. It only reveals one of the two components of the state. Once the agent receives the first confirmation, he optimally does different things depending on what he knows about the other component. He either continues learning from the other source or ceases learning completely. No matter which scenario is optimal, there exists an action that the agent optimally takes when he ceases learning before receiving the second confirmation. I denote this action as AI. This action depends on the agent's posterior beliefs at the time of receiving the first confirmation. Now, equipped with this notation AI, I can formulate the first phase rule. The agent uses the source for which the following expression is greater: the probability a given source produces a confirmation, plus the utility from action AI when both hypotheses are true, times the probability that both hypotheses are true. This rule is reduced to the familiar belief-driven rule when there are only three states and at most one hypothesis is true. The second result can also be extended. When the loss from taking a wrong action in states 1, 0 and 0, 1 is high, phase 1 is relatively long. The only difference is that we have to limit the loss from taking a wrong action in state 1, 1. Intuitively, this condition limits the benefit of getting the second confirmation. In contrast, the first two conditions say that the benefit of getting the first confirmation is sufficiently high. To conclude, I study a single agent's problem, where the agent first learns about the state of the world that has two binary components. After he stops learning, he chooses an action with state-dependent payoffs. The agent has access to two information sources. He can search for confirmation that theta 1 is 1, and he can search for confirmation that theta 2 is 1. I show that the optimal learning strategy has two phases. The main result is that without state 1, 1, the first phase rule is to search for the most likely confirmation. The takeaway here is that this rule does not depend on the payoffs. When state 1, 1 is present, this rule is approximately optimal, and the optimal rule involves the payoff at state 1, 1. The first phase length increases with stakes, that is, with the loss from taking wrong action. This result can be viewed through the lens of a research dilemma and provides some justification from this quote from Robert Aumann. People but too often want to emphasize practical importance, practical applications. And this is not what science is about. Science is simply following your curiosity. And if you're doing interesting things, then eventually it will find its applications. In research, the stakes are usually high. Hence, the first phase rule is optimal in the near future. And when choosing the research question, we should follow our beliefs, or as Robert Aumann suggested, our curiosity, rather than being guided by payoffs, that is, practical importance of our potential findings.